I'm going to start today by just briefly reviewing Wednesday. This is all recorded and posted on YouTube. This is it's a pretty important concept to get down. The example we went through on Wednesday will also be really, really helpful for your homework problem number 1 that's due next week. So previously we had derived the heat equation and come up with that second order partial differential equation that varies, where temperature varies in time and in space, which allows us to solve for the temperature profile through a solid or a stationary medium. So in chapter 3, we're getting a little bit more specific. We're taking the heat equation and coming up with simplifying assumptions and solving it for the temperature profiles of some specific cases. And in chapter 3, we're focused on one-dimensional steady-state conduction. So we took some one-dimensional steady-state conduction examples. We've started with the plane wall, which is just heat flowing through a wall where the cross-sectional area normal to heat transfer is constant. So we went through and we tried a couple of different ways of coming up with an equation that looks like this. You can also get to that same point by starting with, so we did this shell balance method to come up with that equation. We also started with just the heat equation. We simplified terms and came up with the same equation here, which reduces to this if you have constant thermal conductivity. So then we then solved that equation. We applied boundary conditions, and by doing that we were able to get an equation that told us the temperature through the wall at a specific distance into the wall. Okay, so I would consider that very important to go back and review that lecture from the 28th, because that'll be an important concept to digest for exams, but you'll also need that to be able to do problem 1, which is kind of an involved problem. Okay, so we also started talking about something called thermal resistance. So we solved for the temperature profile of, which is, you can see this here. If you have 2 different surface temperatures on a plane wall, if there's no generation, and if you're at steady state, and you have constant thermal conductivity, this is what your temperature profile equation looks like. It's just heat flux through, it's basically just the equation of a line. So here's your intercept, your slope is delta T over L, and then as you vary with x, your temperature changes. So if we took this temperature profile and applied Fourier's law to it, so let's just, okay. So if we have a plane wall and we know TS1 and TS2, if those assumptions apply, again, steady state, no generation, constant thermal conductivity, our solution is just a straight line. So we have this straight line. Sorry. We have this straight line going through our system, and that equation is just our temperature as a function of x, where x basically starts here at the left side of the wall and goes into the wall, is equal to TS1. I'm going to cheat here. So we have TS1 plus this delta T times x over L. Okay, so this is a specific solution to the heat equation for these specific assumptions. This is pretty much as simple as it gets, but there's quite a bit of things you can do by knowing what this temperature profile looks like. So we have the equation for temperature. So if we wanted to solve for flux or for total flow of heat using that temperature profile equation, how would we get there? If we wanted to get flux as a function of x, so flux in the x direction as a function of x, how do we go about getting that knowing this temperature profile? What'd you say?
Isn't it just the Fourier's law, but instead of the temperature, at whatever it's temperature, the thing you're looking at minus the temperature.
You're doing great. So Fourier's law, let's start there.
Yeah.
Okay, so what is Fourier's law? We have minus k times dt dx. Okay, so we have a function that is t of x, so we would just solve it for dt dx, and we would then just multiply that by negative k, and we'd get flux as a function of x. So this dt dx is the slope of our temperature line, right? So that slope for this particular system, under those particular assumptions, is constant. So we have this constant slope. So our temperature line has a constant slope, which means we're going to have constant flux. So this guy is just going to be equal to some constant. So our flow of heat through the wall is just going to be a flat line. And I do this, and the book does this, and someone has asked a question about it, but often you'll see these kind of diagrams like this. So this is basically what this is. It's a plot of temperature superimposed over a diagram of the system. So we have basically x and y. So we have a plot of temperature, but then we also have this diagram so you can see how that temperature lines up with your wall. So you'll see that a lot, and I sort of just take it for granted, but I just wanted to back up and make that abundantly clear. I'll do this frequently in the class, and the book will also do this. Okay, so I started off by talking about thermal resistance. So if we can think back to some of the introductory lectures, what is the driving force for heat transfer? It's a temperature difference. So whenever there's a temperature difference through a media or from one medium to another, there's going to be heat transfer from hotter temperatures to the cooler temperatures. So knowing that as you're going through this wall, knowing that your slope of your temperature line is constant and you're going to have constant flux, you can actually develop kind of some shortcut methods. So we've used the heat equation to get to this point where we have this temperature profile. There may be times when we don't really care about that temperature profile. Maybe we only care about how fast heat is getting through it. So this thermal resistance is a really convenient way to solve certain types of problems quickly. You would use this thermal resistance method to be able to quantify the flow of heat through a medium. It gets really convenient when you have multiple modes of heat transfer in series or in parallel. This is a great method to help you solve more complex problems. However, you miss out on the detailed temperature information, like temperature versus X kind of information. So for a plane wall, there's something called actually, let me get into my notes here and make sure I explain this well. Okay, so our flow of heat, because if we took Fourier's law, knowing that that slope is constant, we can express this same heat flux term. So knowing that the flux is constant through the whole wall, we can express this differently as basically delta T over L, where L is the full thickness of the wall multiplied by K. So our flux can be expressed for this particular system with those particular assumptions. We can make this case. So the thermal resistance gives us another way of writing this, where we can express the heat transfer as delta T over this term that I'll define called the conductive thermal resistance. And there's a couple of different forms. So basically this thermal resistance method says I know that there's a temperature difference between point A and point B, and when those particular assumptions apply, again, steady state, no generation, constant thermal conductivity, I can take this simpler form of the equation to quantify the flow of heat. Yeah, Caleb? This, I'm ignoring it because this, I'm just sort of treating this as flow of heat regardless of direction. So I'm kind of, it's a little bit hand wavy, but I'm not really concerned right now with the vector form of the heat flow. Okay, yeah, Blaine? There are different forms of this. So right now, so flux is minus k dt dx. If we wanted to talk about total flow of heat, we would multiply this by the cross-sectional area and this by the cross-sectional area. So we're keeping it in this flux form right now, but by multiplying through by area, you would convert that to the flow of heat kind of form. So the idea of thermal resistance is that from point A to point B, you know there's a delta T. And so all that material in between, you come up with a thermal resistance term to represent all of that. You don't necessarily get all the information about how the temperature changes through that medium, but you come up with this simpler way of quantifying the flow of heat. So if we look just by inspection, thermal resistance, how is it defined for conduction through a plane wall? Someone say that again? Yeah, so L over K. All right, so we're sort of just doing this by inspection. You'll see the convenience and the utility of doing something like this when you start to solve problems where there's multi-mode heat transfer and there's a lot of different things happening. Okay, so let's think about this for a minute. Let's think about just a wall. Let's take this room and pretend like we're dividing it in half by, let's start with a thin wall. It's 10 centimeters wide and it's made out of wood. Okay, so if we wanted to have more, okay, we got this wall dividing. Let's also say this side of the room is really hot and this side of the room is really cold. So there's going to be this flow of heat from hot to cold. And we got this thin-ish wood wall dividing the rooms. So if we wanted to make less heat transfer happen, what would we do in terms of the thickness of that wall? We'd make it, making the wall thicker, so increasing L, is going to increase, it's going to increase the conductive thermal resistance, which in turn, as we increase that, when we increase the conductive thermal resistance, we're going to decrease the flux through the wall by making it thicker. Okay, so now let's take that wall that's made out of wood and let's interchange that with a wall that's made out of steel. So by your intuition, would steel have a higher or lower thermal conductivity? Okay, so steel is going to have a higher thermal conductivity, which means as this gets higher, then our conductive thermal resistance is going to get lower. So the steel wall would have a lower thermal resistance, which means heat is going to flow through it better. So with that lower thermal resistance, when this gets lower, our flux is going to get higher. So just to provide a little bit of intuition there. So this thermal resistance method allows us to have kind of we sort of ignore everything that's happening actually in the wall, but if we know the surface temperatures, then we could still quantify the flow of heat by taking the material properties both K, which would be just sort of an inherent material property, and L, which could be something we designed by making the wall thinner or thicker. And taking those material properties and dimensions, and we could still quantify the flow or the flux of heat through the wall without having to go through all this business of solving the heat equation and getting the temperature profile. It might sound fairly trivial now because this plain wall is as simple as it gets, but this really comes in handy when we deal with radial systems or systems where there are lots of different flows of heat happening at the same time. Any questions so far? Okay, so this is a new slide that if you have the slides downloaded, I'll post this when I post the annotated slides after today's lecture. So we're going to use this thermal resistance as a tool. It doesn't solve every problem, but it solves certain problems. So you've got to learn what problems this might apply to and how it can be useful. It won't always be useful, but sometimes it will. So it's based on the idea that when you have a delta T, a fixed delta T from point A to point B, and that you know that the flow of heat is constant based on certain assumptions like steady state and no generation, you know it's constant with respect to space and time from one point to another, you can still quantify the amount of heat flow in terms of a temperature driving force. So we can get our flux is going to be equal to delta T over R total. Or we could also get just our total flow of heat is equal to delta T over a different form of R total. So the terminology and the units get a little weird. It's just a matter of convenience. So flux is the flow of heat per unit area. So you have to use a corresponding resistance. So the little double quotation marks will sort of help you align flux with this form of resistance. And that is referred to as the total, the thermal resistance for unit area. It's not per unit area. The units end up having watts squared in the numerator instead of the denominator. Just know that when you're dealing with flux, you want to use that form of the thermal resistance. And when dealing with total flow of heat, you want to use that form of thermal resistance on the right. Okay, so this only applies at steady state. It only applies when there is no generation in the media, because if heat is flowing through a wall and that wall generates energy, that means there's more and more energy to deal with. So the flow of heat as a function of x is no longer constant in that case. So this method falls apart. It doesn't apply. It doesn't work. Okay. So it allows you to ignore temperature profiles through the medium and calculate the flow of heat just through the medium when you have these two temperatures on the ends. So it makes it much easier to calculate the flow of heat through multiple media in series and or in parallel. Yes?
So this has to do with materials R factor when you go to like Home Depot and buy insulation?
Yeah, perfect. That's exactly what this is.
Or Windows U factor?
It is, the total resistance is the inverse of U. They're definitely related. So for anyone who has experience in construction, if you buy insulation, it's given an R value. So because its function is to insulate, do you want that R value to be high or low? Okay, I heard a good mix of both. You want the R value to be high. Higher thermal resistance means it's a better insulator.
It's not that R total.
I think it may be, it's going to be the R double, it's going to correspond to the R double prime. Because the total area, so you go to, if you guys have ever seen that fiberglass insulation, it comes in these big rolls. You got to roll it out and stick it in the walls. So depending on how much insulation you would buy, so that the total area over which you're applying the insulation to would factor into the total thermal resistance. So you'd be using, the values you would see would correspond to this guy, because this is sort of independent of area, whereas this one is dependent on area.
So you want to keep what's below, though, if you want it to have high.
Yeah, so the reason you'd buy insulation is to keep heat in your house or out of your house, depending on if it's summer or winter. So you'd want a really high R value, some really good insulation, and so that you reduce the flux. If you're air conditioning your house, reducing that flux means you're losing less of your cold. Let's switch to winter. When you're heating your house, you're losing less heat because you have this better insulation. So you will have different thermal resistances whether we're talking about conduction or convection. So for conduction, we looked at this already, but let's think about it again. This guy is L over K, and this guy is going to be L over K times A. So when you have a much bigger area, if you're putting insulation on all the walls of your house, you make the A bigger. Oh, wait. Yeah, that's right. Okay. So you make the A. No. You're making the area that the insulation is applied bigger. Give me a second here. Yeah. Okay. Oh, yeah, sorry, I'm not, yeah. Okay, that's not a great explanation. Anyway, so if you're insulating your house, you could go buy really cheap, crappy insulation that might have a K value that's too high. So one approach could be you just add multiple layers of it. So you're making L bigger. You're just adding thicker and thicker insulation. You're still getting to the same point. Or you could just have something that has a really small K value, and you'd get the same insulative properties without having to make it thicker and thicker. Okay, so it's something we'll cover. You'll have a lot of problems that we'll solve together, and we'll put a lot of thought behind this, and this will start to sink in for you. Okay, so we started with the heat equation. We solved the heat equation to get our temperature profile for a specific instance. So once we have our temperature profile, you can differentiate the temperature profile and multiply that by the thermal conductivity, and you can actually calculate flux as a function of X through the wall. But that's, for this particular system, when it's a plain wall, it's just a one-dimensional system, we'll find that temperature profile is just a straight line. It's not that way when those assumptions do not apply anymore. So we've talked about the thermal resistance for conduction in a plain wall. So it's L over Ka. There's also a corresponding convective thermal resistance, which is just 1 over H times A. So when you're thinking about our house and we're trying to heat it in the winter, there are actually going to be 3 different modes of heat transfer happening. We've talked about this before. So you'll have, if you got your house here, you have this air temperature inside, and then you also have this air temperature outside. So for you to actually lose heat, you would take that hot air is going to have to first convect to the inner wall of your house. So we'd have to convect from this air to the inner surface of the wall. Then that heat is going to have to conduct through the wall here, and then it's going to have to convect out again. So even though that seems like a really simple problem, losing heat from your house out to the ambient air, there's still three different modes of heat transfer involved. So we can represent that by using what's called a thermal circuit. And here's where we would add up our thermal resistances. So this is what a thermal circuit looks like. So you have these nodes. These nodes represent a temperature somewhere. So this would be, let's call that the inside air temperature. Okay, and then this one would be, what would this be? If this is inside air temperature, what would this one be? This would be the inside wall temperature. This is going to be the outside wall temp. So we distinguish between a surface temperature and a fluid temperature because there's still a mode of heat transfer to get heat from a fluid to a surface or vice versa. And that heat transfer happens by convection. All right, and here we have the outside air temperature.
So is this problem dealing with convection and convection?
Yeah, so this is quantifying. We talked about, so let's get there right now. So the nodes represent temperatures in our system, and that's all happening in series in this particular example. So these resistors represent thermal resistances. So we talked about this one. That is the conductive thermal resistance of heat trying to propagate through the wall and then back out to outside. So this on the left that's the convective thermal resistance on the inside of your home. And then this on the outside is the convective thermal resistance on the outside of your home. So you'll see this form. It's important. So the nodes represent the temperature of that medium at a specific place. And then the resistors represent a thermal resistance. So if you wanted to make your walls thicker, let's say you take your normal walls and then you start slapping on, in a really crappy way, just insulation on the outer surface of the wall, you'll be adding more thermal resistance to your wall. So adding more thermal resistance to your wall, what's that going to do? It's going to decrease the flow of heat. So as you add insulation, you're adding more thermal resistance, which means the flow of heat is going to decrease. So I say all that to make the point that for thermal resistances in series, you add those resistances to get the total resistance. So here you would have this convective thermal resistance added to your conductive thermal resistance, and then add that to this other convective thermal resistance from the outside. Any questions there? So if we want to calculate the flow of heat from inside your house to outside, this thermal resistance method is a really nice method to use, where all you need to know is the temperature of the air inside your house, the temperature of the air outside. You actually don't even need to know what the wall surface temperatures are, but you do need to know what the wall properties are, the thickness and the thermal conductivity. So I hope you're starting to see the value of this method. We can calculate the total thermal resistance from one point to another point. In this case, the air inside our house to the air outside. We can express that as just a delta T, and then it's just a matter of calculating the total thermal resistance. And notice these are all just constants. In homework problems, you'd be given the H's and the L and the K, and then you'd calculate the areas, but this would be a constant. Any questions there? Yeah, Caleb?
Is there a read thermal resistance?
Yep, there is. I don't find it to be quite as useful because radiation is nonlinear. We won't really use that until there are different methods for dealing with radiation and the nonlinearities. There's kind of an analogous method that we'll get to at the end of the semester. Okay, yes, and what's your name? Ivan.
I understand how we got the L over K times A
Uh-huh.
for the resistance for the conductivity, but I don't know how we did it for the 1 over H times A.
Okay, that is because I forgot to do that. Okay, thank you. So remember, this thermal resistance method, we want to express our flow of heat as delta T over some thermal resistance. Let's call this, I'm going to give this a subscript CONV for thermal resistance by convection. Okay, so if we wanted to go back to another method, what's the rate law you guys know for convective heat transfer? So let's look at Newton's law of cooling now. So keeping this in the flow of heat terms, we have, help me out here. Hopefully you guys are starting to get this. It's HA times delta T. So the convection is already in this really simple algebraic form, so it's pretty easy to get. So just by inspection, we would get that 1 over the convective thermal resistance is equal to HA. Or the convective thermal resistance is equal to 1 over HA. So really you can just arrive there by inspection of these two different rate law equations. So Newton's law of cooling, which we're hopefully getting familiar with, and then all we're doing is rearranging Newton's law of cooling to put it in this form, which may seem a little bit pointless right now, but once we start doing things like adding these thermal resistances together, this gets much more convenient. Okay, questions there? Okay. So if you take out the area, then for conductive thermal resistance, you get this thermal resistance for unit surface area. It's not per unit surface area because this is the inverse of something that is per unit surface area. It's just, the thing to remember is when you're dealing with flux with the Q double prime, then use this form of the thermal resistance for unit area. So a conductive system, it's just L over K. And if we wanted to convert our equations instead of dealing with flux to dealing with flow of heat, we would add the A. Well, we would actually divide this term by the A, which is equivalent to multiplying our transfer equation by A. So there is, to Caleb's question, there is a radiative thermal resistance. So it involves dealing with that linear form of radiation, like that. But if you remember, to calculate that radiative heat transfer coefficient, that's a function of temperature. So this is still a nonlinear equation. I don't find this to be particularly useful. Radiation, you have to deal with the nonlinearities, and this only applies and is useful in a few select instances. Okay, so there is also something called contact resistance. And that has to deal with when you have two different solids that touch each other, there's some interface between the two. Often there's sort of a poor connection between those two materials. However, this gap may be microscopic. And so there may be bad heat transfer from one solid to the other solid. So there would be this sudden jump in temperature. And of course, there's going to be a lot going on the microscopic scale, but we'll just call that a contact resistance. So if we looked at a temperature profile, again, I'm doing this thing where I am plotting temperature as a function of x, but I'm also going to throw a drawing of what's called a composite wall in there. So let's say we have wall A and wall B, and let's say that interface between A and B, there's a really, really poor contact. So if we plot a temperature, this is a plane wall with all the assumptions that we've talked about. So you might have your temperature goes like that through material A. Then there's this sudden jump in temperature because of that void space. And it might jump to that, and let's say B looks like that. So basically, we're sort of saying we don't really know or care what's going on at this interface, but we can measure this thermal contact resistance, and so we'll just put that in there. So it's, you could get down to the microscopic scale and try to apply Fourier's law and try to quantify like an effective conductivity here, but this is another convenient mathematical tool where we can just say there's just a sudden jump in temperature because there's poor contact there. So often when you solve problems, this thermal contact resistance will just be given to you as a constant. So you might say, what's the flow of heat from here to here, so that our total resistance is going to be the conductive thermal resistance from material A plus this contact resistance plus the conductive thermal resistance for material B. So in simple terms, it's just you don't know exactly what's going on here, but you might just give it, hey, there's a contact resistance there. And it's hard to put it in terms of Fourier's law because this might be so microscopic that there's not really a measurable delta X or thickness. So it's just, you represent that mathematically as just this sudden temperature jump. But you could still calculate the flow of heat by just calculating this total resistance through conduction, then contact resistance, and then conduction of material B. Okay, so we will often deal with composite walls where there are a wall, we've talked about this example of your house. Well, the walls of your house aren't just a single slab of wood. You have drywall, you have insulation, you have studs in there, you have more drywall, you have siding on the outside. So you can get these more complicated things happening. So we'll do more complex analysis by considering composite walls, where we'll want to calculate the total thermal resistance through that entire wall, but also include the convective thermal resistances from the outside of the walls. This gives rise to something called the overall heat transfer coefficient. Actually, I'm going to backpedal a little bit. So let's look at this wall. We got those three sections, A, B, and C. So we're going to have conductive thermal resistance through each of those sections. We are neglecting any contact resistance. We're making the assumption that all of those walls that, for example, A and B, that interface is really nice and smooth and it doesn't disrupt the flow of heat at all. Same with B and C, but we could certainly add in contact resistance in there and make this even more complicated. The good thing is that pretty much all you do is calculate all the different thermal resistances and add them up. So you would calculate the thermal resistance for convection from the fluid on the left side, and then conduction for the three materials that make up the wall, and then convection for the fluid on the right side. We would just add them all up, then we would get this total thermal resistance. Because it's just a plain wall, if we wanted the total thermal resistance for unit area, we would just divide that whole thing by the cross-sectional area of the wall, and then we could deal with either energy flow terms or flux terms. So this allows us to put our equation back into a form that looks a lot like Newton's law of cooling. So this term is basically Newton's law of cooling. However, instead of H, we're using U. So U is called the overall heat transfer coefficient, and it's basically UA is just the inverse of our total resistance, where A is the area. So we could even get this back into a form that looks like Newton's law of cooling by calculating an overall heat transfer coefficient. This will become important when we deal with heat exchangers, because we're trying to exchange heat from one fluid to another fluid, and it's got to go through some kind of pipe or tube wall. So there's a lot going on there. You can't express the heat transfer in just in terms of convection. So you have to do this thermal resistance method and try and get this overall heat transfer coefficient. So as you start dealing with heat exchangers later in this semester and in design, and for some of you that go into process industries, this overall heat transfer coefficient will be something that you deal with quite a bit. Okay, so I've launched some interactive questions. They should be up already. Well, the first one should be. So we're going to examine, again, this is a plot of temperature superimposed onto a diagram of a wall. So it's basically the temperature is a function of X, looks like that red line, but you can also stick the diagram in there and map where, in terms of X, does that particular location line up with our temperature. So the first question is, just looking at the conductive sections, the solid sections A, B, and C, which wall section has the lowest thermal conductivity? And if you need a reminder, the room name is POW 3453. And it's just the last 4 of your unit is your individual login. All right, so let's get to 30 people, and then let's stop and discuss. Okay, so here's the right answer. Sometimes I'll actually put the right answer in there. So I should have asked this before, but let's say who answered B and wants to explain that for us? Yes, and what's your name? Anna. Can you explain it for us? You don't have to if you don't want to. You answered B. That's good. That's great. Okay, remind me your name?
Kyle.
Kyle.
So I noticed the temperature difference is the greatest in B.
Okay.
And because for the resistance, your thermal conductivity is in the denominator, it's inversely proportional. So the lowest value of K will have the greatest temperature difference.
Okay. Okay, good. Thanks both of you. That's great. Okay, so the way I would explain this is you look at the slopes of the line. So whichever line has the greatest change in, whichever section has the greatest change in temperature, that means it resists heat the most. So section B has that much bigger slope than A and C. So the temperature change through it is greater. So let's think about this differently. Let's go back to imagining a wall here, the wooden wall. And we got this room super duper hot. Let's say we got it to 100 degrees Fahrenheit. And we kept this room super, super cold. So imagine wood. Let's say you're standing on the cold side and you went up and touched this wall. How would it feel? Feel warm. Okay, great. Now let's replace that wooden wall with a steel wall. Same scenario, really hot on this side, really cold on this side. You're on the cold side, you go up and touch that wall. How does it feel now? It feels much hotter than in the wood scenario because steel is a better conductor of heat. So you're going to feel that temperature from the other side a lot better. So the steel would have a smaller slope. It's going to conduct heat really well through it, which in these terms would equate to having a lower thermal resistance to the flow of heat. Does that make sense? I'm trying to help you guys develop a little bit of intuition there. Yeah?
So if we were going with the resistance analog, like the diagram suggests, then we could think of temperature as kind of analogous to voltage, and the and the thermal conductivity as the inverse of the resistance, and the one with the greatest voltage drop would be the one with the highest resistance.
Yeah. Just like in a thermal circuit, when you have higher resistance, you experience a larger voltage drop. Even if the current around it, so current is analogous to flow of heat here. So even if the current is constant, when you have higher resistance, you experience a bigger voltage drop. Yeah. So in heat transfer, higher thermal resistance means you experience a bigger temperature drop. So another way of saying this would be that, well, I brought this up saying you can use this thermal resistance method when you know that the flow of heat is constant. So the flow of heat in this scenario, we get to steady state, there's no generation, there's no accumulation. So the flow of heat through this whole system is going to be constant. So the flow and the flux are going to be the same no matter where you measure that in terms of x. So for the materials that have a higher thermal resistance, you're going to need a larger driving force. So the flow of heat is a balance between thermal resistance and driving force. So if one has a lower resistance, it needs a lower driving force to get the same flow of heet through it. Okay, new question. Very similar, but now we're including the convective thermal resistances on the two ends. So for the whole cross-section shown, which section has the highest thermal resistance? And I guess that last question was about conductivity, but same kind of thing. And I want to finish these before the end of class, so I might just get 20 people to answer, and then let's look at it. Let's get to 25. After 25 people answer, I'll show the results. If you ever want to join this, I can add an account for you, but okay. Oh, hey, we're past it. Okay. All right, hey, this is great. Good job, you guys. So now, because we're dealing with convection and conduction at the same time, so now we would actually, instead of just looking at slope, we'd look at the total magnitude of delta T comparing each section. So you'd look at, for the conductive sections, you'd look at the left end minus the right end and consider that your delta T. So the biggest delta T is in the cold fluid on the far right side. So it has the highest thermal resistance and it experiences the highest temperature drop as a result. Questions there? And I think those who answered B, that's pretty good too, because we're sort of eyeballing this and sort of, so B is probably a pretty good answer as well. All right, last question. Okay, so now which section has the highest heat flux through it? This is at steady state, yep. Steady state and no generation. All right. Okay, so trick question, so they're all the same. So we talked about this. So let's go back to our room scenario. So this is a really important concept to try and get this to sink in. The flow of heat from the left side, that air in this room to the air in this room, that's going to be constant all the way through. And basically we would, if we had our wall here and we turned on this big giant heater in this room, that's going to be our heat source, but that, let's assume the room air is well mixed and that all gets up to a uniform high temperature. So then on this side, in order to maintain that 0 degrees Celsius, we would need some serious refrigeration on this side. So ultimately, heat's going to be going from our heater and being removed by our refrigeration unit on this side, but the flow of heat all the way through is going to be constant. From point A to point B, that flow as a function of x is going to be constant. This doesn't hold up if you're not at steady state because some of the heat's going to be absorbed along the way. Or if somehow the wall generates energy, then you might pick up some extra energy as you go. But when you're at steady state and when there's no generation, that flow of heat is going to be constant. So as we waited for our two rooms to reach a steady state, all the different temperature profiles are going to basically balance. If something has a higher resistance, then that's going to be coupled with a higher delta T. But ultimately, that balance of resistance and delta T will all be equal for every section in this particular plane wall system. Yeah, Nimdo?
So you're like a circuit where you're like, it's a closed circuit, the same current is flowing through even though you get different voltages, it's not like the same current.
Exactly, yeah, yes. Yeah, same current is flowing through it, but your voltage would be different. That's great.